A very quick word before we start the show. There are 2 events coming up in October you should have on your calendar: Transition AI New York and Canary Live Bay Area. The market for artificial intelligence in the energy sector will likely surpass $13 billion in the next 5 years. The tech is moving fast, and Transition AI is the premier event charting how it will shape utilities, renewables and storage developers, energy traders, and EV charging integrators.
There's 50 plus use cases, depending on how you define a use case. There's hundreds of vendors in this space with AI embedded in their products. It's worth billions.
Transition AI New York is a one-day conference and workshop in Manhattan on October 19th. It's going to feature top experts from Microsoft, GE Digital, AES, National Grid, Oracle, and a range of founders, executives, and academics who are building AI strategies right now. Plus, we'll present a detailed market map of the industry, and our podcast listeners get 10% off. Go to the link in the show notes or go to transition-ai.com. Get your ticket for Transition AI New York and use the code PSPODS10 on checkout, and we'll see you October 19th.
You know, there's a lot of work ahead of us, but I think it's there. The technology's there.
And for all you Bay Area listeners, our partners at Canary Media are putting together a live event on October 3rd. It's at Freight and Salvage in Berkeley. It's going to feature a roster of top journalists and experts handpicked by the Canary Media editorial team. They're going to dive into all things energy transition, investments, Inflation Reduction Act implementation, and tech innovation. We recently played a very popular conversation between futurist Ramez Nam and journalist David Roberts. It was recorded from Canary Live Seattle. And if you like that and you like to network and you're in the Bay Area, get your tickets for Canary Live Bay Area. Again, it's on October 3rd in Berkeley. We have a link in the show notes, and those Canary Live events tend to sell out, so go get your ticket now. And now, on to the episode.
From the studios of Postscript Media and Canary Media.
I'm Shayle Khan, and this is Catalyst.
Photosynthesis itself is not very efficient, which is one of the surprises. The global photosynthetic mean is like 0.3% efficient. And this is far shy of the efficiency of like an electric motor, which is like 98% efficient. However, photosynthesis is very robust. It works in a wide range of conditions. So it's resilient. It's not designed for efficiency. It's designed for permanence and resilience and things like that.
Some might say food is energy. Just food for thought.
Let's face it, environmental news is often very depressing. That's why we focus on solutions on this podcast. But still, the climate crisis looms large. Rising temperatures, mounting pollution, environmental degradation, they're all warping the planet. And for a lot of species, including us, things don't always look so great. But the story doesn't end there. Every Friday, Living Planet, a show from Deutsche Welle, takes you behind the headlines to figure out what's happening and how we'll get through it. It'll also help you make better choices for a healthy planet and find space to reconnect with the beauty and wonder of the world around us. You can find Living Planet wherever you get your podcasts.
I'm Shayle Khan. I invest in revolutionary climate technologies at Energy Impact Partners. Welcome. So a while back, I had Dr. Michael Weber on this pod to talk about the water energy nexus, basically all the ways in which our water system is intertwined with our energy system, how they benefit each other, and also how their risks are intertwined, particularly as climate change takes hold. Now it's time for the sequel, because of course those aren't the only two systems of global importance that are tangled together. So this time it's food and energy. Equally important, equally knotted and interdependent. So let's dig into it. As you'll recall from last time, Michael is a professor at UT Austin. He's also the CTO at my firm, Energy Impact Partners, and a frequent collaborator on thinking about big systems level energy stuff. With no further ado, here's Michael. Michael, welcome back.
Thanks for having me. It's always good to chat with you.
All right, so we did the energy-water nexus. Now we're going to do the food-energy nexus. And I've seen you write a couple of times the phrase food is energy. Let's start with that. What do you mean when you say food is energy?
Yeah, at its most basic form, food is energy. It's the energy we need for our bodies, for the power plant of our bodies. And the energy is in the proteins and the lipids or fats and the carbohydrates in the food we ingest. And that's where we get the energy to operate our muscles. So food is energy. It's the most primal form of energy we need for ourselves, and therefore is more fundamental, more important than the other forms of energy we talk about for the other parts of society. So food is energy. It's the energy for us and for our bodies, and animals and plants also need food.
So one thing I've seen a little bit of your analysis on, which I think is interesting, is if you think about food as a form of energy, as you just described, and sort of contextualize it relative to the other types of energy that we think about that power our society, like how efficient, how good is food an energy carrier, source of energy?
Food itself can be a very energy dense material, especially like the lipids and fats are kind of the same energy density as fossil fuels, which is really incredible. And so they like butter and the fatty part of a steak and that kind of thing. Proteins have less energy density, and carbohydrates have the lowest energy density, which is kind of ironic because we think of carbohydrates as a way to get too much energy that makes us fat and that kind of thing. But in terms of energy density, the megajoules or kilojoules per kilogram, the lipids are fossil fuels, you think about it. And the proteins are pretty good, and then the carbohydrates are less energy dense, but they carry this energy, but most importantly, they carry the energy in a form that our bodies can digest. And we can convert that energy into, say, glycogen or stored sugar in our muscles or other energy we have in our body. The gasoline and methane, other energy forms we like for our engines, our body can't ingest and use. So the food we ingest is really energy in a form we can use.
Okay, and so the way that we harness most of that energy for food is in the form of photosynthesis. So if you think again in the context of photosynthesis versus all the other ways that we harness energy, like how good is photosynthesis? How efficient is that?
It's not very efficient, and that's the irony, that all the food system depends on photons ultimately. So we're all living on solar energy. That solar energy in the form of photosynthesis becomes the food we eat, the fruits and vegetables, or becomes the feed for the animals that are food we eat. And so solar energy is the basis of all of humanity and human life. But photosynthesis itself is not very efficient, which is one of the surprises. The global photosynthetic mean is like 0.3% efficient, and really good crops in really healthy areas and ecosystems might be as high as a few percent, maybe 8 or 10% in some places. And this is far shy of the efficiency of like an electric motor, which is like 98% efficient. So our modern human devices are far more efficient than what nature provides with photosynthesis. However, photosynthesis is very robust. It works in a wide range of conditions. So it's resilient. It's not designed for efficiency. It's designed for permanence and resilience and things like that.
Right, but it's an interesting thing to think about. So we'll get back to this later when we talk more about how we use food for energy. But, you know, if you just compare, so efficiency matters in the context of land use, I think, more than anything else. So if you think about how much land it takes to deliver a certain amount of energy through photosynthesis versus how much land it takes to deliver that same amount of energy through, let's just say, solar, in the form of solar photovoltaics, rather, not solar photosynthesis, you get a lot more energy. Now, again, there are different forms of energy for different purposes, but you get a lot more energy these days out of putting solar panels on a space than you do out of growing plants on that space.
Absolutely. You're absolutely right. If you have an acre or whatever amount of land you have and it's hit with photons, you can convert those photons into a useful form of energy, say electricity, with something like 20% efficiency. But if you convert it first into bioenergy, corn for ethanol, then the corn photosynthesis efficiency is a couple percent. And then the biorefinery is not very efficient also. So if you only have so much land and only so many photons to go around, solar panels are generally a more useful, more efficient, and better utility way to go than to go through food crops. So that's an important trade-off, especially as you think of like all the corn biofuel subsidies and mandates and policies we have in the United States or other places. So that's a real challenge. The advantage of bioenergy, though it's less efficient, is you get the storage for free. It's storing the solar energy into the cellulosic materials, which is kind of handy. That means you don't have to use it the moment the photon hits. You use it some number of days or weeks or months or years later. So that's kind of handy, but you pay a pretty steep penalty for that.
All right. So as we did with the energy water nexus, with the food energy nexus, we're going to talk about all the ways that we use energy for food and then all the ways that we use food for energy. And then we're going to talk about the nexus between those two and how it's changing. So let's start with how we use energy for food. First of all, how much energy do we use to produce food?
It's a big number in the United States. It's about 10%. Different people do the analysis and come up with anywhere between like 8 and 15% of national annual energy consumption is for the food system. And for the food system, I'm including at the field, agriculture and the agrochemicals that go there, the diesel for the machines, the propane for drying the crops. Then you use diesel to transport the crops to a milling location or a factory where there's processing and grinding. And then it might go to a refrigerated warehouse, then it's delivered to a grocery store. Then we pick it up in our gasoline car, and then we cook it with natural gas or electricity. Then we dispose of the food waste. And if you add up all the energy embedded in the chemicals, like the pesticides and fertilizers, as well as the fuels to operate the crops, not even including the solar energy, like just the sort of man-made fuels or the man-refined fuels that go into the system, it's about 10%. So it's a big number. And 10% of that, or 1%, is in the food itself. So the food we need to ingest in the United States is about 1 quad of energy a year, and we consume about 100 quads of energy over the course of a year. 1 quad of that is in the food we eat, but there's another, say, 9 quads of energy to grow and reap and harvest and improve and cook and process and dispose of that food. So it ends up being about 10 quads overall.
Do you have a sense of how that has evolved over time? I mean, not back to like, at some point we were exclusively eating locally and not transporting anything, and presumably it was a much lower number. But, just over the past few decades, like, is that number, that 10%, is that increasing or decreasing?
It has been mostly increasing since World War II because of the additional agrochemicals made from things like natural gas, in particular the fertilizers and the pesticides, but also the diesel for the mechanized tractors. If you go back hundreds of years, it was all manual labor. And so we were growing food mostly to get the energy we needed to grow more food. And so the amount of energy that went into the system in the form of our manual labor was not much more than the food itself. And we'd also do some gathering and hunting and that kind of thing. We didn't always have to grow the food ourselves directly. And so that's a big part. We've added energy inputs along the way. So the energy requirements for the food system have gone up a lot. But as a consequence, food productivity has gone up a lot. So we can grow much more food per farmer and much more food per acre, so that today a small fraction of society is growing food for the rest of society. So 1 or 2% of society as a farmer, for example, can feed the rest of the nation, so to speak. And that's because we replaced the manual labor with these additional energy inputs. So it's a good news story from that productivity. It was the first green revolution. We're talking about a green revolution today. Well, agriculture already did it decades ago. And that enabled more people to become artists or other things because we're getting so much food per person. And that's because of the energy inputs.
All right, so we traded less people, more energy for the same amount or more food. So breaking down those sources of how we use energy for food. So you mentioned that 1/10 of the energy we used for food is actually in the food. Let's just talk through the other categories with a little bit more detail.
There's another percent or so of national energy consumption, so I would say another 10% of the food energy that is on the field for fertilizers and the fuels for the combines and tractors and that kind of thing. There's another couple percent of national energy consumption, or another, say, 20% or so of the food system's energy requirements for transportation to move the food from the farm to the factories, from the factory to the grocery store, from the grocery store to our house. There's another 10% or so in food manufacturing, processing, refining, milling, cutting, chopping, that kind of thing. And then another 40% of the food system's energy requirements, or 4% of national energy consumption, is in the cold chain and in the cooking. And so the cold chain is a really big part of this, and that's refrigeration at the grocery store, refrigerators and freezers at our homes, refrigerator warehouses and other places. That cold chain helps preserve the food, which is a good news story. We didn't have that cold chain 130 years ago, really. So that's a good news story, but it's very energy intensive. And if you just look at the United States, our cold chain is a few percent of national energy consumption. We use more energy for our cold chain than countries like Switzerland and Sweden use combined for all purposes. So you could run entire countries, multiple rich countries, with just the energy we use for our refrigeration in the United States. And that's something that you don't have in such a common way, say, in sub-Saharan Africa or Southeast Asia. So this is sort of unique to richer areas where they have that refrigeration to keep the food preserved.
And then I guess the other category that seems important to me is, and you mentioned it originally when you talked through all the things that we do at the end, is the food waste. How do you think about food waste as it relates? I mean, obviously food waste, there's lots of problems with it, right? Food waste becomes, if it biodegrades, becomes methane. It emits, a powerful greenhouse gas. From an energy perspective, how do you think about food waste?
Food waste is a big issue for all these reasons. It takes up space in the landfill. It generates greenhouse gases. It also wasted the energy that was used to grow it. And that food waste number is something like 30 to 50% of the edible food in the United States is thrown away. Typical numbers say 40%. Similar numbers in, say, the UK and other rich countries. So there's an incredible amount of food waste. And it's certainly a problem at the end of life when it decomposes and makes methane, but I think of all the energy that went into growing this food that we don't eat. And we don't eat edible food sometimes because we don't feel like it, or it's ugly fruit. There are these ugly fruit and vegetable campaigns, go ahead and eat the ugly tomatoes. They still taste good and they're still healthy and this kind of thing. So there's a lot of energy embedded in that food waste. And reducing food waste would be a very good thing for us to do because it would avoid all those environmental impacts. And I would say also that food waste happens in a different stage of the supply chain in the United States compared to, say, a poorer country. So in the United States, we have a very robust cold chain, which is good news. But that means we're wasting the food on our plate. We're over-serving at these all-you-can-eat buffets, and then we just don't eat it. Or we don't take it home with a doggy bag. Or we put it in the fridge but never eat it. The food waste is happening in poor countries earlier. It's not wasted at the plate. It's wasted on the field because they can't get it to market quickly enough, or they have post-harvest waste because they can't refrigerate it. So the waste happens in different stages depending on where you are in the world. But the waste is a problem any way you slice it because it's resource-intensive and then environmentally impactful.
All right, so we've got this in some ways, this broad category of 10% of energy is used in the food world, in food, and it comes in all these smaller slices that we've just kind of walked through. What do you think about the kind of big systemic changes that could reduce that energy consumption overall? For example, the buy local movement to reduce presumably the energy consumed in transport, plus probably some of the cold chain, things like that. What do you think are, if any, realistic systemic changes that we might make if we decide we're energy limited?
I really like buy local, and my wife does too, and we do it for a variety of reasons. We love to go to the farmer's market. We love to meet the farmer who raised the animals or grew the food. We think it's good for the local economy. We think it's good for food security. We like it philosophically, just for the connection to the food. We feel like we're too far away from the food, so we like all that. But it's not necessarily better for the environment, and that's a surprise for many people. So we do it for all these other food security or philosophical and spiritual reasons. It can actually be very energy intensive depending on what you grow. So local food can be really good for the environment if it's locally appropriate food. But there are a lot of foods that are grown locally that aren't appropriate. I think of in Saudi Arabia, they grow a lot of tomatoes and wheat in the desert, and this is not locally appropriate. They improve their food security, which is why they do it, but they have to add a lot of inputs, electric pumps for irrigation, a lot of chemicals, a lot of things to grow it in the desert. It would be much less energy intensive to import the wheat and tomatoes from other areas of the world where it grows more naturally. So there's sort of this tension that local food is actually one of the big priorities to reduce energy impacts of the food system, but it doesn't always work out. You got to think about, well, what is it you're growing locally? And there are these famous examples of wine from France delivered by ship to New York is less energy intensive than the closer wine in California moved there by truck. So you have to think about your transportation mode. Or lamb from New Zealand eaten in the UK is actually less energy intensive than the local English lamb because the lamb in New Zealand is grown just off of rain-fed grass. Whereas in England, we'll have a lot more feed, and the lamb in England are moved to market by truck. But the New Zealand lamb is moved to market by ship. So you have to think about what you're growing, how you're growing it, and then how you're shipping it. And certainly the shipment of lamb from New Zealand to the UK increases your transportation energy requirements, but lowers all your other energy requirements and works out to be beneficial, which is sort of interesting. You get these non-obvious outcomes. And I'm a big local food fan, but I have to sort of turn a blind eye to the potential energy and environmental risks on that because I'm doing it for other reasons.
What about different types of food? So, for example, obviously there are other emissions-related reasons why, for example, we might want to eat less beef just because of the emissions in the cattle world, but maybe not specific to beef. Are there big differences in terms of the energy intensity, the energy embedded in different types of food, or at least categories you think about?
Absolutely. And when we think about systemic changes, which was your sort of question, where you think, okay, what can we do? Well, reducing waste, we talked about, is a very big one. Changing what we eat or how much we eat of it also is very important. The transportation miles tends to get the most attention, but actually is not as important. A great study came out of Carnegie Mellon over a decade ago looking at sort of these food miles. And the conclusion they had was that food choices, meaning the diet selection, what we eat and how much we eat of it, is much more important than the number of miles the food moves, which is kind of interesting. And that's not obvious for a variety of reasons. And that's one reason we have like fruits that are always in season. We get them from somewhere, but if they're moved by ship, it's not that big a deal. And these grains and fruits and vegetables tend to be much less energy intensive than the proteins, the animal proteins. And so probably, at least in the United States, we eat a lot of beef, we eat a lot of meats, and I'm a beef eater and I really like eating beef. We could all probably stand to eat a little less protein and that would be less impactful. The good news of the meat world is that we tend to waste less meat because it's so expensive. We tend to waste other things that are sort of less expensive fruits and vegetables that don't have good shelf life, but they're not as energy and environmentally intensive. So we have more waste on the things that are less impactful, less waste on the things that are more impactful. But without a doubt, animal protein is much more intense, at least the way we do it today with conventional approaches. And there might be some new approaches we can look at with, say, beef or other animal protein that are less intensive.
Okay, so let's flip the script now. We talked about how we use energy to get food into our bodies. Let's talk about how we use food to get energy to power our society. So how do you think about the big categories there?
The big ones are the bioenergy feedstocks that we are starting to use for fuels. And the prominent ones these days are sort of corn for ethanol, sort of alcohol that we can use to blend into gasoline for combustion engines. In the United States, we use a lot of soy to get biodiesel, and in Europe and elsewhere, you might use palm oil to get biodiesel. And corn and soy and palm oil are sources of calories for a lot of people, for food around the world. So we're using that food to power up an SUV or a truck or something instead of feeding people. And this creates all this food versus fuel moral dilemma, which is super challenging. And it has all sorts of land impacts, and it might not even be that good from a CO2 perspective. So it's super controversial and a place of great argument, but that's one of the main ways that we use food as a form of energy. And that's why there's a push, at least by the scientific community, and scientific community has been pushing for this since like the 1970s, to use non-food feedstocks or non-food sources for alcohols we can use for sustainable aviation fuel using cellulosic sources, things that we can't eat because we can't digest it instead. But there's a lot of food for energy with these different biofuels, essentially. We can use some waste. We can use corn stover or other parts of the plant that we wouldn't eat anyway. That's a cellulosic source as well, so we can think about that. There's also some different people who looked at capturing carbon, capturing CO2 from power plant smokestacks and turning that into baking soda to make cookies. And I kind of laugh like, okay, I don't think we need 40 billion tons of baking soda because if we ate that many cookies, like we'd all die for other reasons. But there's this idea that we can use the waste products from the food system as a useful sort of material or ingredient or as a form of energy as well. And one of the waste products is the manure from animal agriculture can generate methane, which is a great source of biomethane. So that's not using the food for energy, but it's using waste from the food system for energy. Or the sludge, the sewage you and I generate that goes down the sewers to the wastewater treatment plants can also generate biomethane. So there are some waste streams we can use from the food system for energy, or we can use the food itself for energy. And we got to think about that because the food versus fuel moral dilemma, I think, is actually worth some more scrutiny.
Do you think, just to put it simply at the highest level, as a society, should we be ever using edible plants, corn, soy, palm oil? Should we ever be using any of that for the purpose of energy as opposed to for the purpose of food?
So in my opinion, no. I don't think we should be using edible food for modern fuels. I think we have other options. Using the waste streams gives me no heartburn. We should totally do that. But I don't like the idea that we're using corn that could feed a lot of people to power up inefficient trucks. Like we could probably achieve the same savings just by making those trucks more efficient or driving smaller cars or driving less often. Like there are other ways to displace 10% of our gasoline consumption, which is about where we are with corn-based ethanol. So if the goal is to displace 10% of gasoline, let's use those other techniques rather than using food. It really makes me nervous. That doesn't mean alcohol fuels don't have some value. They have some value to increase sort of the performance of the engine. You can get higher compression ratios, you can get less pollution, this kind of thing. So there are some benefits. But if we believe electric motors are going to displace those gasoline engines anyway, what's the point? So I'm really critical of using food for fuel that way when we have so many other options. In the United States, efficiency is a great starting place.
Okay, so we've talked about how we use energy to get food into our bodies. We've talked about how we use food to produce energy. There, I guess the key distinction I'm understanding you to be making is there's edible food we basically shouldn't use for energy. Waste products from the production of edible food, whether that be corn stover or something else, that actually we might as well do something with because it's a waste product otherwise. And if it has value as an energy source or in a different context as a source of biogenic CO2, then great, right? But separate the waste product from the primary purpose of the crop. Is that right?
That's exactly right. Yeah, and there's a lot of waste streams in agriculture, and especially things like manure and crop waste and things like that. Well, let's use that. Some of that crop waste is used as a soil amendment to keep the dirt from floating away or running off, that kind of thing. But we have especially hundreds of millions of tons of manure that we could turn into biomethane as opposed to just leaving it as an environmental hotspot, a liability. So there are these waste streams. We might as well use that in a way that helps us avoid other energy or reduce emissions elsewhere. So I really like that. But growing food for the purpose of energy gives me all sorts of discomfort. I should have said gives me all sorts of indigestion. That was the obvious pun, right? So I should have said that.
Good point. All right, so let's just talk about the ways in which this nexus between food and energy is changing. Obviously, maybe the biggest, highest level one is climate change itself. So what do we know about the ways in which climate change will affect the food energy nexus, or either is affecting it today or will affect it as climate change worsens?
Climate change really is a challenge for agricultural productivity. Above a certain temperature, photosynthesis really drops in efficiency. So that's one challenge. The droughts and floods either wash off the soils or hamper the ability for the crops to grow in the first place. We're having massive agricultural losses in Texas right now from the heat wave and drought. They can't get the feed for the cattle, so they take cattle to market before they're at full weight, so they get less money. Like, it's a huge problem to agriculture, how hot it is today. And then you also have different pests have 3 reproductive life cycles in a summer instead of 2, so they can eat the crops or sort of cause other problems. So there's a lot of challenges to agriculture from climate change directly just on crop productivity and health of the ecosystem and that kind of thing. You might get some improved agricultural opportunity in northern climates. So maybe for a while we'll see improved agricultural outputs in Canada, but then those will be offset as well later on. So there's some disbenefit in certain latitudes and benefit in other latitudes, but more harm than good overall from climate change itself. But then you have these other steps of the system. You might need to air condition more of the crops to keep them from spoiling. The heat accelerates spoiling. So we're spending more energy on air conditioning to prevent that spoiling. And it just kind of accelerates like we do for everything. We need more air conditioning for our homes anyway. So this is a challenge. It looks like we'll spend more energy to overcome the consequences of climate change, to make up for the lost productivity or to store the food and the crops. That's a real challenge. And we're already seeing, like, we have massive losses in Texas and elsewhere from climate events. And it's not just the heat waves. The freezes kill citrus crops. And the thing about climate change that's ironic is we have milder winters, but are more likely to have these intense deep freezes too. So we get it on the winter, then we get it in the summer, and it's just a real challenge. And then we have this sprawling global food system where maybe it hits Texas, we'll say, okay, no problem, we'll just get our fruits and vegetables from Chile or somewhere else, but other countries will be hit as well. So this is a real threat to agriculture in many ways. The nice upside looming we could talk about is agriculture might also be one of the solutions to climate change if we think about uptake of carbon into soil and changing the farming practices.
Yeah, is there an argument that we should just... So, okay, if one of the... I haven't really thought this through, so admit this is half-baked, but at a high level, if one of the impacts of climate change is just going to be lower productivity on balance across the board, means we're going to need more land to produce the same amount of food. But simultaneously, as you said, there's a benefit to agricultural soil from a carbon uptake perspective. And some plants, perhaps not the ones that are meant to be eaten, but other plants can be used for carbon removal and so on and so forth. Should we just be pushing for more agricultural land? Like globally across the board, or terraforming parts of the world that don't currently produce anything?
That's a great question. I mean, I think without a doubt, if we had to choose between more strip malls and parking lots or more agricultural land, I would like more agricultural land. It's prettier to look at. It provides a variety of ecosystem services. So I think that'd be great. And some of the solutions you mentioned might be we need more land if productivity goes down. We might not need more land. We might need more energy inputs. So this is the tension, right? Do we overcome the productivity challenges with more energy in, like more fertilizer, or with more land to make up? And I don't really know the answer on that. But I think agricultural land, if we flip the script and say, well, let's pay farmers to take CO2 out of the atmosphere rather than pay them to produce as many kilograms of protein as possible. Like if we change sort of the remuneration scheme so there's more payments for more services they provide, then they can grow protein, but maybe instead of at a feedlot, a really concentrated feeding operation where you have a lot of cattle in one spot, you go to these sort of advanced multi-paddock systems where you have more cattle in more places. There are some analyses just actually they will be carbon negative on life cycle because what the cattle do, if it's not too concentrated, will improve the soil health and take CO2 out of the atmosphere. And so I don't know enough about this because I'm not a soil scientist or an agricultural scientist, but the people I talk to say, actually, agriculture can be part of the uptake system, but we're not rewarded for it. There's no incentive to do it. For us, it's all about pounds of beef per acre or something like that. That's the incentive. And so getting there with prices on pollution or maybe incentives for deploying some pilot projects to RD, there are other ways to do it. And I wouldn't be surprised if we decide that more land for nature and more land for agriculture is better than more land for parking lots.
All right, so I guess final thread of questions here. Everything we've been talking about assumes this direct relationship between the environment and the climate and our ability to produce food, which is true when we're growing crops outside. There's obviously this other very emergent sector of indoor agriculture, which sort of breaks that link. So, but on the other hand, one of the arguments against indoor agriculture, particularly the fully closed environment agriculture, as opposed to greenhouses, is its energy intensity, because you need to use a lot of power to power the LED lights that, mimic photosynthesis, et cetera. So how do you think about that in the context of this nexus?
There are these sort of technology trends that happen in the food system and in agriculture. Electrification we're seeing in a variety of places. There's food delivery services now, like during COVID, we got everything delivered. Why not get food delivered? And that's sort of interesting whether it's worse or better. There's indoor agriculture. So there's a lot of different trends underway. In indoor agriculture is pretty interesting because it's a shift from the liquid forms of energy, diesel for the tractor, and the liquid chemicals you apply, the pesticides and fertilizers to the field. By going indoors, you shift that to electricity. So it's electrification of agriculture. You could also electrify agriculture with, say, electric tractors and electric on-field synthesis of ammonia. There are other things you can do with electrification, but indoor agriculture is a shift from those chemicals and fuels to LED lighting, because you probably don't have enough photons at that site if you're doing sort of multi-level indoor agriculture, as well as maybe some pumps to circulate the water and some blowers and that kind of thing. So it's a huge demand for electricity. It increases your energy requirements. However, you avoid the chemicals because it's a closed environment. You can control the pests better. And so you don't need the chemicals. You don't need the pesticides. And for a lot of people, they don't want the pesticides on the food they're eating, especially fresh fruits and vegetables. And because it's indoors, it can be sort of temperature controlled and humidity controlled. You can get better productivity. But it's also more comfortable for the food workers, the agricultural workers, the laborers, because they can work at a shelf that's chest height rather than stooping down the field. They can actually use the bathroom rather than having to go in the field near our food. So it's much better from a labor justice perspective. It's much better from a chemical perspective. It's much worse in terms of electric intensity. So that's the trade-off we're going on. And it ends up being pretty expensive. So we wouldn't do it for the bulk commodity crops like wheat or corn. But for fruits and vegetables, that might work. And by the way, they don't have to be hydroponics or aeroponics. It could be just greenhouses like they do in the Netherlands, where they control the environment. The Netherlands is, I think, the number 2 exporter of food by value around the world because they grow a lot of high-value crops, flowers and fruits and vegetables in an indoor setting. And so it's a big shift in kind of what form of energy we're using, what kind of things we're growing with it, but we get these other benefits. But it might not be an energy savings overall. It might just switch it to a form that's easy to handle and easy to decarbonize, which is electricity.
All right, Michael, bit of a teaser for our next one. So we've done water energy nexus. Now we've done food energy nexus. What's another one that you think is important?
The next one you already talked about is land, right? We think about food and water and land as sort of the tension we deal with when it comes to energy, because a lot of the energy options we want might be really good from a water perspective, and they might be good from a food perspective, but they're land intensive, say. So that's the next sort of tension to think about. And food's at the nexus of all of this. It's really the food, energy, water nexus, potentially. But land is on my mind because, generally speaking, the renewable sources of energy that are popular because they're cheap and they're low carbon tend to be more land intensive. And how we integrate that will be pretty interesting with food. That's like a whole field of agrivoltaics, where you have solar voltaics together with farming, and you get these interesting things where you're getting electricity out plus food, and the plants cool the panels, so the panels are more efficient and productive, and the panels shade the crops so they grow with less solar damage. So you get these enhanced sort of productivities from integration if you take land into consideration as well.
Agrivoltaics, people, that and photovoltaics, people often tell me that we should do an episode about. So someday, maybe we will. But okay, land energy nexus comes next. In the meantime, thank you so much for coming back.
Thanks for having me. It's always a great conversation with you.
Michael Weber is a professor of mechanical engineering at UT Austin and the CTO of Energy Impact Partners. This show is a co-production of Postscript Media and Canary Media. You can head over to canarymedia.com for links to today's topics. Postscript is supported by Prelude Ventures, a venture capital firm that partners with entrepreneurs to address climate change across a range of sectors, including advanced energy, food and ag, transportation and logistics, advanced materials and manufacturing, and advanced computing. This episode was produced by Daniel Waldorf. Mixing by Roy Campanella and Sean Marquand. Theme song by Sean Marquand. I'm Shayle Khan, and this is Catalyst.